Alright, in this video what we're going to do is talk about Duhamel's method. We just finished talking about the convolution, and now we're going to put the convolution to work for us. And what we want to do is we want to solve the differential equation x prime of t minus 3x of t is equal to f of t, where I'm not going to tell you what f is, right? I want to do this just for a general function f. Here we want x of 0 to be 0 and x prime of 0 to be 0. So we have our two initial values. And what we're going to do is we're going to throw everything that we have at this problem. We're going to need a few things here. So we're going to start obviously by taking the Fourier transform of both sides, the Laplace transform of both sides. So if we take the Laplace transform of x prime of t minus 3x of t, and that's going to be the Laplace transform of little f of t. And let's see, if we take the transform of the derivative, that's going to turn out to be, so we have to go back and look at our table, but that's s times capital X of s minus little x of 0. And this is going to be minus 3 times capital X, right? If we just take the transform of little x, we get capital X. And likewise, the transform of little f is capital F. Okay, capital F. All right. What we're going to do now is try and solve for capital X. Remember that I think I'm given one too many of these. I think we don't need I don't see how this is going to enter in the picture. Maybe we'll come back and we'll add it if necessary. But I think x prime of 0 equaling 0 is superfluous. So what we're going to do now is try and solve for capital X. Remember that little x of 0 was 0, so that little x of 0 actually cancels. And what we're left with, so this implies that s minus 3 times capital X of s is equal to capital F. And what we can do then is we can take the s minus 3 term and divide both sides by s minus 3. So we end up with 1 over s minus 3 times capital F. This looks pretty difficult to solve, but remember what we know is that the Laplace transform of a convolution, so f convolved with g, is the product of the transforms. And therefore, if I were to take the inverse Laplace transform of a product, what do we get? We get a convolution. Okay, so we end up with f convolved with g of t. And that's exactly what we're going to do. So now we'll take the inverse Laplace transform of both sides. So we're going to take the inverse Laplace transform of both sides. And when we take the inverse Laplace transform of capital X, we end up with the input function, which was just little x, which is what we're looking for. And when we take the inverse Laplace transform of a product, this is going to be the convolution of the inverses. So this is going to be the Laplace transform inverse of 1 over s minus 3 convolved with the inverse Laplace transform of capital F. Now the inverse Laplace transform of capital F is nothing more than little f, just based on our convention. And then we need to think about what's the function whose convolution is 1 over s minus 3. In other words, what's the inverse Laplace transform of 1 over s minus 3? And that's nothing more than e to the 3t. And our final step is I want to actually write out this convolution as an integral. So x of t we can write as, if this is a convolution, this is going to be the integral from 0 to t, e to the 3y, f of t minus y dy. And what we've done is we've taken and solved our differential equation. So this, I think this is pretty cool actually, but we've taken and solved our differential equation here. Okay, so we've taken and solved that differential equation for an arbitrary function f. So now what we can do is, if I were to just add on to this one extra step, let's say I want to solve x prime minus 3x equals, it doesn't really matter what we want, make it as crazy as you want it to be. X prime minus 3x equals, let's say, sine of x squared. Something that we're in no way going to be able to, sine of t squared, I mean. Something that we're in no way going to be able to actually find explicitly. Well, what we can do is we can run through the same process, and it turns out that x is going to be the convolution of e to the 3t with our function little f. So that's the integral from 0 to t, e to the 3y, sine of t minus y squared dy, right? And then that gives us a nice formula for the solution of our differential equation. Okay, this again is called Duhamel's method.